When you throw an old lithium-ion battery into a recycling plant, recovering those valuable metals takes hours of grinding, cooking, dissolving, neutralizing, and filtering. It's a chemical marathon. But the scientists at Rice University, led by James Tour, can do the same job in just a minute. Not with more chemicals, not with enormous furnaces, but with a blinding electric pulse that reaches temperatures hotter than a volcanic eruption, and forces the material into a non-equilibrium state where the metals resort themselves. So let's take a look at the difference between the conventional method, equilibrium chemistry, and this new Flash Joule method of non-equilibrium physics. And if you stick around to the end, you'll see why this new process doesn't just beat the old one. It breaks a limit we didn't even realize existed. I'm Ben, this is Physics or Bust. So the first question to ask is, so why do we care? Lithium, cobalt, nickel, and manganese, the metals in lithium-ion cathodes, are expensive and critical for batteries, EVs, and the energy transition. But current recycling is slow, water-intensive, and uses really strong acids, which results in high energy usage and lots of waste. For a battery economy to become circular, recycling needs to be cheaper, cleaner, and more efficient. Conventional hydrometallurgy, the dominant route, is basically just dissolve and separate. You grind the battery to a powder, leach metals into strong acid, then use staged chemistry to precipitate or extract each metal. Physics and chemistry here are at equilibrium or near equilibrium. We'll dig into the physics in a minute, but first, if you like this video, you'd probably like this book. I've got a link in the description below. I do get a small commission, but it wouldn't cost you any extra. Put simply, with equilibrium chemistry, we set conditions, wait for the reactions to reach a balance point, and then isolate. Separation is controlled by solubility and redox potentials, what dissolves and what stays solid. And then you nudge the equilibrium to favor one metal at a time. The Rice group flips the script. Instead of slow equilibrium chemistry, they blast the mass with a fast electric pulse. They call this Flash Joule Heating. And while they shock this mass with electricity, they're exposing the sample to a chlorinating environment. That instant of extreme conditions forces the material into non-equilibrium states, where they behave differently than under slow heating or acid baths. The outcome? Lithium becomes a soluble chloride, while transition metals convert into oxides or other phases that are not water-soluble, letting you separate the lithium quickly through simple water wash. So looking at the physics, there's two key features that make the flash approach work. The first is ultra-rapid heating. The sample is driven to extremely high temperatures in milliseconds to seconds. At these temperatures, kinetic barriers disappear. Reactions that would normally take forever run instantly, and volatile species can form and move before the system relaxes. The second is non-equilibrium pathways. Because the heating and cooling are so fast, the material doesn't have time to reach equilibrium. That lets you access reaction pathways and products that are thermodynamically possible only at extreme conditions and are kinetically trapped when you cool quickly. In this case, lithium is driven into chloride form and remains mobile. Heavier transition metals end up in oxidized, less soluble forms. So the Rice method is kind of a physics magic trick. Use time and temperature as control knobs to force a different chemical sorting mechanism than the slow one we rely on. So let's break down these two steps even further. Flash Joule heating with chlorination takes about 60 seconds. An intense current pulse heats the black mass. In the presence of chlorine or a chloride donor, lithium forms lithium chloride, and other volatile species can be driven off or transformed. The heating is so fast that elements are selectively converted based on their transport and reaction rates. Step 2, oxidation. After the flash step, a controlled oxidation converts the transition metal chlorides into oxides while leaving lithium as lithium chloride. Because lithium chloride dissolves easily in water and many metal oxides don't, the simple aqueous wash pulls out the lithium, separating it from nickel, cobalt, manganese, and the graphite anode material. And the fact is, results matter. The team reports that graphite, cobalt, and lithium can all be collected with high yield. The paper shows about 85 to 97% yields on the key materials and about 99% purity on them. And the critical point is time and reagent use. The flash process happens in seconds to minutes, uses much less solvent and reagents, and avoids hours of acid leaching and neutralization. The paper's life cycle and techno-economic analysis signals large reductions in energy use and operating cost compared to standard routes. Alright, so all this sounds amazing, but it's not magic and it won't be easy to implement in a factory setting. There's 4 main issues to work through before factory scale adoption. Chlorination requires careful handling and off-gas capture. Real plants will need scrubbers and corrosion-resistant engineering. The published experiments are gram scale. Industrial continuous feed requires reactor redesign and material handling engineering. Black mass variability, different cathode chemistries, and contamination will require process tuning. And last, they're going to have to do a pilot plant to really test this out. If this scales, it could make recycled lithium cheaper and more available, reducing reliance on mining and lowering the environmental footprint of batteries. That would do things like make EVs more affordable and lower the need for mining to keep up with the demand for lithium. For physics nerds, it's a great example of how controlling time and temperature can be just as powerful as controlling chemicals. Now, when we look at limitations, conventional methods are bounded by equilibrium thermodynamics. Most people don't realize that with this old process, you can only separate materials as far as their solubility and redox potentials allow. And you end up with a fairly substantial amount of material that you just can't separate from the waste. But non-equilibrium forcing can change those rules. By accessing pathways that are only favorable at extreme short-lived conditions, you can cheat the limits that equilibrium imposes. That's why the Rice method doesn't just speed up the old chemistry. It breaks the limit that chemistry puts on the old process by using physics to change the rules. I've linked the paper and the Rice press release in the description below if you're wanting to dig into the methods and numbers yourself. If you like this breakdown of science and tech, make sure to like and subscribe. I really appreciate you guys watching, and the best way you can help this channel grow is to watch this video right here. And remember, keep asking questions. I'll see you on the next video.